Ringrazio naturalmente per l'invito, è un piacere, al di là della retorica, essere qui per fare questa lezione voltiana. Vedo tante persone che conosco e ringrazio naturalmente per questa presentazione che ha fatto Michele. Io vi parlerò appunto in inglese delle onde gravitazionali. So I will switch in English just to tell you about this the opening of this new astronomical window, the gravitational wave window. Let me start by reminding you what happened on the Earth on September 14, 2015. That day we received and measured the first gravitational waves coming from a very peculiar source in the sky. You know, the waveform, the shape of a wave brings a lot of information. Suppose you enter in a dark room and you don't know what there is there. You don't see nothing. At a certain moment, someone plays a note in a piano. Then, immediately, you recognize that in that room there is a piano, and even which note has been played, and if you are quite expert, you even can distinguish if the piano is good one or if it's economic, cheap, let's say. So the shape of a wave brings a lot of information. So it's not a surprise that this wave told us many things on the source, on the instrument, if you want, that were in the sky. And this was the instrument, this was the source of this wave. We knew that there were two very large mass objects, 36 solar mass one, 29 solar mass the other, that were very compact, very small, only 100 kilometers of diameter, two very concentrated mass, incredibly. We know all that, and we will see better in the rest of the talk how it is possible to know all this. But it's more or less the same, that a surprise like knowing that there is a piano and there is a note in a dark room. So what we can reconstruct about the source is this. There were these two black holes which were rotating one around the other, and this is quite slower than the original. I mean, the original was much faster, but this is just to appreciate this dance of one black hole respect to the other, and at the end of this dance they fuse each other. All these generated gravitational waves arriving on the Earth on 2015, but generated there in that point in the sky 1 billion, more than 1 billion years ago. You see that you don't see, because no photons came from this source, no electromagnetic wave. So we know about this source only through gravitational waves. But what is gravitational waves? Well, let me start, since this is a lecture, and I think we have, well, not 1 hour, a little bit less, but let's say we have some time to develop and to appreciate how human beings arrived to these nice results, fundamental results. This is the notebook of an Italian, of Galileo Galilei, which was reporting on a certain day a surprise, I mean a new discovery. Now I like to show this because I consider this date, 7 January 1610, the beginning of the modern astronomy. Up to that moment, astronomy were made by naked eye. So you knew about the universe not only by the light, but the nearest light, let's say. So in particular, you knew that there was Jupiter, a very important planet there. But what Galileo discovered, pointing the telescope, the cannon, as we call him, to the sky, was a surprise, was something new. When you develop a new instrument, you always have something new, and most of the time this was not predicted. In fact, this was not predicted. What is all? Let us read in Italian that a D7 di gennaio 1910 Giove si vedeva col cannone, che è appunto il nome che si dà al cannocchiale, e 3 stelle fisse così. So 3 fixed stars, 1, 2 and 3. This is I, see the director of Jupiter. So, and he says, delle quali senza il cannone niuna si vedeva. So it was a discovery. 3 lights that were not reported by Babylonians, by Egyptians, by Greeks, by the Bible. No, nothing. It was the discovery of the ignorance. And it is the beginning of the modern astronomy, because it was not only a surprise, but even more. After that, he says, a D8, so the day after, appariva così. This is Jupiter, and the 3 stars moved. This was even more incredible. Not only there were new stars in the sky near Jupiter, but the stars moved with respect to Jupiter. This was absolutely incredible. And then he also says that the motion is in the opposite direction respect to what the calculator says. In modo diretto e non retrogrado, come dicono I calcolatori. Calculatori were the people calculating the position of these objects in the sky. A D9 era nuvolo, punto. The day after was cloudy. But he says that, you see, it is important to report. This is something very simple, but it is important to understand that discoveries are made by scrupulous reporting of what you see, what happens. Even if it was cloudy, he could have not written that it was cloudy, okay. No, he said that the day 10, we know that near Padua in 1610, the day of 9 of January was cloudy. And then the day after, the day 10, you see there was again, they moved and one of the stars was in front of Jupiter. So it was the incredible discovery that that Jupiter was a solar system in its own, a small solar system in its own. Why this was incredible? Because the Copernican revolution was very, very recent. So the sun, following Copernicus, had this special privileged role to be the center of a local universe, or everything around the sun, not around the earth. And this was already a revolution, of course. But this is another revolution, because Jupiter in its own has this privilege in itself. This is the first sign of the universality of gravitation. And in my opinion, from this point on in the history, nothing was like before. It was the beginning of a long trip. Then came Newton and gave to this observation a mathematical form. I mean, with Newton, we understand universal gravitation. We understand even mathematically. And this is a drawing, like before, it was the original manuscript of Galileo. This is an original drawing of Newton. And in this drawing, there is a fantastic synthesis of the heaven and on the earth. Up to the time, our mentality, I mean, the way of looking to the universe was that on the earth there were some phenomena, terrestrial phenomena, dirty phenomena, and in the sky there were the pure heaven phenomena. So different nature. With this drawing, we understand that there are no two physics, there are not two different natures. This is only one physics in all the universe. And this is why, because he says simply that if you throw a stone from the top of a mountain, the stone, of course, falls on the earth. This is a common experience. If you throw with a higher speed, then it falls a little bit farther. If you throw with stronger, let's say, it will fall a little bit farther again. And if you fall a little bit more, then it continues to fall forever. It continues to fall forever without meeting the Earth, because the Earth has some finite dimension, of course. But why this is revolutionary in itself? Because he understands that the moon is falling on the Earth. This is why the moon is there. Why the moon is always there, near the Earth, but not going away. Simply with the same law that attracts stones on the Earth, that makes us being fixed here on the Earth. It's the same solution, the same reason. So the reason was then written mathematically through the gravitational force, in which, as you know very well, the product of the masses divided by the square of the distance between the two masses. And with this mathematical form, we know why the solar system is there. We can predict where a certain planet will be in 1,000 years. This works very well, Newtonian mechanics. It was really a fundamental step in the history of philosophy, of natural philosophy, of physics, not only of science. Then arrived another man which said that actually the force of gravity does not exist, really. So this is even more surprising, and you need to explain why. First of all, why Einstein thought that Newton was wrong. He thought that because the Newtonian mechanics and the Newtonian gravity had a problem. The problem is that gravity was fixed to the source. If the sun moves, all the gravitational field moves with the sun, propagating the information that he is moving at the speed infinite speed. So the gravitational field is in a sort of prisoner of the source. There is no way. Just everything is it knows immediately that what the movement in the sky. This was not in the following Einstein. This was not reasonable in a way. He knows at that time already that the Coulomb force has the same expression of the Newtonian force, but with the electromagnetic field, what happens if this electric charge moves, then a wave propagates and the electromagnetic field propagates at a certain speed, the speed of light, which is extremely large but not infinite. So the fact that the gravity had this infinite speed of propagation was not it's not symmetric with respect to the electromagnetic case. And then also other reason, but let me in this lecture goes to the heart of the various issues. So following Newton, the explanation for the gravitational attraction is not the presence of a force, is that the presence of the masses deformates the space-time around, and this deformation causes all the other masses, the planets, to go free but constrained by the curvature of the space-time. So in a way, the presence of the sun makes the space-time no more flat. What does it mean, flat? That following Newton, this is a mass attracts everything. But if a ray of light passes here, it goes straight. And if a ray of light passes there, it goes straight. The space-time is flat. You can give two laser light parallel and they go parallel forever. Well, following Newton, this was not right. I mean, the presence of a mass deformates the space-time around, and if you put a small mass here, it goes around this one, not because of the presence of a force, but because of the deformation of the space-time around. In a very synthetic way, as John Archibald Wheeler said, space-time doesn't matter how to move, matter tells space-time how to curve. This is the equation of Einstein in a very compact form, and it's quite difficult to understand. But let me make a simple comparison just to understand what we are speaking of. The comparison which I made is this equation with another equation which all the students should know. I think it's much more simple. It's the equation of a spring and a mass. If you apply a force and this mass is connected with a spring of a certain elastic constant, K, which said how stiff is the spring, then there will be a deformation, X, which will depend on the force applied and on the elastic constant. So this is the expression of the force. It reacts, the system reacts with the force in the opposite direction respect to the one of the force applied. And so the comparison is that the force has the same role here of this. This is the tensor, the energy tensor, let's say, this mass energy tensor here. So the cause, the source of the deformation, and this is the deformation. So in the Einstein equation, the metric tensor, let's say, what gives you the geometry of a space-time depends on the presence of energy and masses all around. So the force here is like this tensor there. The X is the deformation, so it plays the same role of the metric tensor here. And K, which is the elastic constant, which say you how stiff is the spring, it is equivalent to this constant here, which say you how stiff is space-time. And what happens is that space-time is very stiff. Is the stiffest thing in nature, if you want. And this is because C is big, G is a small number, so the elastic constant of the space-time is incredibly high. It's very difficult to deform space-time. I cannot deform space-time with an object like that. I have to deform space-time with the very big mass, like the sun. And how I see the effect of this deformation? The Earth goes around. This is the effect. The Earth goes free. No force. Just it follows what is the minimum distance in the space-time which is deformed by the presence of the sun. And this was demonstrated in a wonderful experiment by Arthur Eddington in 1919. So this is the position of a star. This ray of light will go straight following Newton. But following Einstein, the presence of the sun gives a certain curvature to space-time. And so from the Earth, the apparent position of the star is there. It's no more here. So what Eddington did was to have an expedition in an island in the Atlantic Ocean in 1919, where a total eclipse was predicted. And the presence of the star around the sun, when the moon was on the sun, of course it was possible to see the star around, was in a different position. They were in a different place respect to the position they had without the sun in this position there. So it demonstrated that actually Einstein is right. and that every mass, every presence of a mass or a star in the sky or even a planet deforms space-time. So for a sun, the deformation is relatively small, sufficient to see the planets around him. But we can think of objects which are more dense, and then this gives a deformation to space-time which is more pronounced. You can think of white dwarf, neutron stars, or black holes, which are the object that also are the more strong gravitational wave sources. And for each of these objects, you can think of a certain deformation in space-time. Now, the black hole is the extreme object in which the gravity on the surface is so strong that not even a photon can go out. A black hole following the Einstein equation is different from a black hole in Newtonian mechanics. You can say black hole in Newtonian mechanics. Following Newton, you can imagine to have a black hole, of course. In fact, the Reverend Mitchell in 1783, with only Newtonian mechanics, it is a very simple calculation that it is possible that a mass, if it is concentrated, may have a surface gravity so strong that not even light can escape. This is because every object, every planet, every star has an escape velocity. And this is clear. If we want this object goes away from the Earth, not returning anymore, I have to give to this object a kinetic energy much greater than the potential energy of attraction that the Earth has on this object. So it is very simple to show that if you follow here, the m is the small mass that want to escape from the planet, then if the kinetic energy is larger than the potential energy, m escapes. But not even the light can escape if you have that the escape velocity is the one of the light. So the object m, which is squeezed inside a certain limit radius, will appear completely dark. And the condition following Newtonian mechanics to have a dark star called John Mitchell, then Archibald Wheeler said a black hole, but it is the same object. You see, for every mass you can imagine a certain radius, the Schwarzschild radius called then after Einstein, which it means that if you want the Earth to be a black hole, then you have to squeeze the Earth in a small sphere of 1 centimeter diameter. If you want the star, a mass like the star becoming a black hole, you have to squeeze that in a 3 kilometer size sphere. It's very difficult to have a black hole, of course. It's not simple at all. Following Einstein, there is a difference. That a black hole is not simply an object which is compact enough and able to not escape even the light. Following Einstein, when a mass collapsing arrives to this limiting radius, it goes straight to the center, the point at the center. This is an infinite curvature right at the center of this object. So a black hole following general relativity is not a black hole following Newtonian gravity. A black hole following general relativity is a relatively big, is a bubble, black bubble, empty inside. All the mass is concentrated at the origin. If you pass the limit of this radius, the event horizon, then space and time reverse each other and you cannot stop. You go directly to the center. Now this is something which gives to the black hole a very fascinating nature, of course. And this is what happens, what we thought happened in the sky. So I said it's difficult to squeeze an object. Certainly, artificially, say it's impossible to squeeze an object. But nature in the universe may squeeze masses and realize these compact objects that was imagined. For instance, if the star is an average star, then it passes various steps in the cycle, becoming a very compact object, but not a black hole, a dying star, something which is simply something which fades with time and becoming very concentrated. If the star is massive, massive says 10 solar masses, for instance, then at the end of its life, it collapses and the mass may be so big that the squeezing force can realize a black hole, can go beyond this event horizon limit and form really a black hole or a neutron star. Now I have no time to go further on that, otherwise I will employ all my time, but it's incredible to see that a star lives for billions of years in a sort of equilibrium between two opposite tendencies. One is the gravity, which makes the more compact and compact, and the other is the nuclear reaction in the interior, which gives radiation coming out, and the radiation which tend to expand the star. So you have these two opposite tendencies. During this life, the star forms from hydrogen all the other elements. Arriving to the iron, it stops. This fabric of elements, this fabric of the periodic table of elements, it stops, and at that moment, without any more the radiation coming out, the gravity wins and the object collapses, implodes, bounces, and makes all around, going all around all the elements formed. So carbon, oxygen, hydrogen, ourselves, we are made like all the planetary system of stars exploded somewhere here in this part of the universe. What remains from the collapse may be stars made of neutrons, because electrons falls on the nucleus, neutralize protons, so there is a big nucleus, solar mass nucleus, or if the star is bigger, it can form what I call a black hole. So this is the revolutionary way of Einstein to see gravity. And the year after his general relativity theory, he solved his equation with a simple approximation, which is called the weak field approximation, in which he imagined the space-time to be almost flat. I mean, there is only perturbation, which is in modulus much less than 1. So this is a almost flat space-time. Then, if you have this weak field approximation, the Einstein equations simplifies a lot, and the Einstein equation takes the form of a known equation in physics, the D'Alembert equation, which is the high solutions of waves propagating in space at the speed of light. So a gravitational wave is a perturbation of the metric traveling at the speed of light. There are some main features, which are they have two transversal polarization states. They are associated with massless spin 2 particles, which are gravitons. These are different from the photons and from the electromagnetic case. In electromagnetism, there exist two types of charges, plus and minus. And in gravity, there is only one type of charges, only attracting. This makes some difference, and the difference is in the spin 2 particles and in the shape of the polarization that you can expect. And I will show you in a moment. Another interesting fact connected to this, what I said, is that a source which lose energy because of emitting radiation has no the dipole term, which is the first non-null term in case of electromagnetic case. If you expand the energy lost by a system, the first term, the dipole, is 0 in the case of gravity, and this is connected to the fact that the linear momentum is conserved, and then there is not possible that exists a dipole term in this radiation. So the first non-null term is the quadruple one. This means that the source has to do something like that. I mean, it is a tidal shape that it is important. So the amplitude of the wave depends on the quadruple of the source. And you see here the difference, the comparison between polarization in the electromagnetic waves and polarization in the gravitational case. So the gravity makes this tidal movement while propagating in space. This is the original paper of Einstein predicting gravitational waves, in which he calculates the amplitude, the possible amplitude of these waves. And he says, I don't know how many of you know German. I don't know German, so I mean I translated in English. He says, in any case, one can think of A, the amplitude, will have a practically vanishing value. Einstein understands that space-time is very stiff, and that it is very difficult to have a large amplitude wave propagating in space-time. So, gravitational waves was considered a curiosity, but not really something that you can detect, that you can try to see. And even in the 50s, there was a debate raging. Are gravitational waves real? It is a real, true physical effect that we can measure, or it is a coordinate effect that you can put to 0 with the change of coordinates. Now, it is incredible to see that Einstein itself was in the field of the people thinking that gravitational waves was not really something which you can measure. It is interesting, this point. But in 1956-57, this was the beginning, if you want, of the experimental detection of gravitational waves, because at that time there was not, in 1957, there was no discussion of black holes and neutron stars. These were objects were not known at that time, but the debate was if gravitational waves were real and if they could be measured. So Felix Pirani points a transparent connection between the equation of geodesic deviation and the Newton's law, and identified the curvature with the Newtonian potential. So this was the clear moment in the history of the detection, because at that point it was clear that if a gravitational wave arrives in a system in which there are 2 points, these 2 points moves one respect to the other, and if you have a ray of light going back and forth, then the time taken by this rate of light will be larger or smaller depending on the amplitude of the gravitational wave. This was the key point, I mean, in the history of gravitational waves. And immediately, some people, like Joe Weber, thought a possibility of detecting, how you can detect. For instance, with a laser interferometer, in which you can measure the distance between mirrors using the light, or with some sort of spring with two masses, an oscillator, a diapason, we would say, that the gravitational waves was put in vibration more or less like a hammer, like a driving force, a driving term in an equation of harmonic oscillator. In both cases, gravitational waves could be measured. This was the effect on a test student, we have here many students, will be that passing a gravitational wave passing through a student will have this effect which is not so evident, of course, and this is why it took 50 years of experimental efforts to detect gravitational waves. So let me go directly to the heart of the lecture, and to try to understand what are the objectives of gravitational detection. First of all, we have to test the Einstein prediction of the existence of gravitational waves. Then the second is that through this probe to gravitational waves, thanks to gravitational waves, we could understand the sources. Are there existing black holes, neutron stars, and all these fantastic objects or not? Then cosmology. Also, this is very important because you see, when you think on the history of the universe, you have to understand that every messenger decoupled from the primordial plasma in different epoch. For instance, photons decoupled at when the universe was already 380,000 years after the Big Bang. This is the cosmic microwave background. Neutrinos decoupled after 1 minute, more or less, of the Big Bang. But gravitons decoupled immediately after the Big Bang, 10 to the minus 43 seconds. So this, if we are able to detect a background in gravitational waves, we have an approach to really to the Big Bang. This will be very difficult, and we are not ready to detect this background. So we have focused the attention of the data analysis to the astrophysical sources. Astrophysical sources like, well, everything which accelerates and has a quadrupole moment will generate gravitational waves. For instance, in a supernova, which is the explosion of the star, then in a millisecond scale time, there will be a sort of burst, an impulse, millisecond duration, which will propagate, giving this information. A spinning neutron star. So if a neutron star forms and it rotates because angular momentum tends to be conserved, of course. So if a star rotates slowly, but when it is compressed and squeezed, it rotates much faster. This is something which all we have experienced in a rotating seat, for instance, by moving weights near to the body or far to the body. And in this case, the wave is a sinusoidal shape, which is modulated by the movement of these sources and the detector. This is the source which is the best known, what people like more, because it is a very clear analytical waveform in which two compact objects spiral together. They emit gravitational waves, so they lose energy, they go nearer and nearer, they acquire, because of the conservation of the angular momentum, they go faster and faster, and at the end they merge. So this gives rise to a waveform which we call chirp, which is something which increases in frequency and amplitude. And this shape tells us the masses of the two objects. And the amplitude at the moment of the merger tells us the distance of the source. Once you know the masses, then the amplitude at the end depends only where is the source, if it is near or it is far. So it's a measure of the distance to the source. And it is very important because with that method, we could determine Hubble constant independently from the other measurements. In fact, if you know which is the galaxy in which the source is, then you know the redshift of the galaxy, you know the distance of this galaxy because of the gravitational wave amplitude, then you know the Hubble constant. And at the end, this is stochastic background I told you already. So this is the man starting this research in the US, is the dreamer, really. He was not the only one, as in Imagine in the song. He was a dreamer, but he's not the only one. In fact, during the 60s, in Italy, Amaldi tried to push the Italian physicists in the direction of new researchers at more in the birth phase. One is the stochastic background, the infrared background radiation, and the other is Penzias and Wilson, and the other was gravitational waves. And in Italy, these two activities started almost simultaneously at that time. In Rome, Amaldi has an assistant, Guido Pizzella, and he became the leader of the group. Thus, this in Italy was always in the first row in this research. This is a picture which I like. This is Edoardo Amaldi when he was 80 years old. So we developed these resonant masses, this diapason that have to resonate when gravitational waves arrived. This is, for instance, Explorer at CERN. All these three people, myself, Fulvio Ricci, Piero Rapagnani, we are now Virgo and LIGO-Virgo collaboration, because you see, when you start knowing experimental methods for putting a mass isolated from all the rest and trying to measure its position, then this kind of skill is the same for all the gravitation experiments. Italy is very, when I say it was always in the first row, all the field is coordinated by Gravitational Wave International Committee, and these are the chairs of the Gravitational Wave International Committee during the years. The first was Barry Barish, which is now Nobel Prize. The second was Massimo Cerdonio, Italian. The third was Jim Hoff, and then was my turn. So two Italians in five, because now Sheila Rowan, which is Scottish, the new chair. Another demonstration, if you want, of the position of Italy, that's the most important conference, the reference conference in this field is named after Edoardo Amaldi. Well, let me try to show you which is the detector with which we detect the gravitational waves. So I start the final part of my conference showing some animation. So this is a laser interferometer. So how it works? It is quite simple. This is a schematic layout, of course. So this is the laser. This is a beam splitter. So the same beam goes in two perpendicular directions. It is reflected by the end mirrors, and so it is recomposed here. So what goes to the photodetector in this case is 0, because you see you have regulated the distance in such a way to have opposite phase. But if one mirrors moves in counterphase respect to the other, you see, so if a gravitational wave arrives, you see that the interference changes and there is a positive interference. And this is a very sensitive method to see if the two mirrors moved, so to see if gravitational waves arrived. So this is the laser interferometer. Is a Michelson interferometer, which was, of course, perfectionated during the years. There are several sources of noise, of course. One is at low frequency. In the low frequency band, this is the amplitude that you can detect, and this is the frequency of the wave. In the low frequency part, you are dominated by seismic noise. You have to reduce seismic noise, of course, suspending the detector very well with mechanical filters. In the intermediate region, you have the thermal movement of the wires and of the mirror, and in the upper part, you have the shot noise due to the counting of the photons of the laser. So there are several interferometers like that in the world. 3 of them are working. I mean, the 2 LIGO detectors and Virgo. They take data together. First LIGO, which was funded 2 years before Virgo. So first LIGO, and then also Virgo. Then there is a smaller one in Germany, and there is a new project in Japan, which will take data in a couple of years. So the real laser interferometer is more complicated that I showed you before. I mean, the light go back and forth in circulating power cavity, and there are a lot of tricks. But what is important is to understand that there are these 3 systems of advanced detectors in the world: 2 LIGO in the US and Virgo in Coccia, which is funded by NFN and CNRS mainly, but is now a full international collaboration with also other countries in it. So to go at the sensitivity able to detect gravitational waves was a long work, a long effort, and you need to have better seismic isolation, you need to have better text masses, perfect mirrors, suspension made by low dissipation material, high power laser with very low noise. So at the end, we succeeded. And the LIGO-Virgo collaboration, thanks to the 2 LIGO detectors on September 14, 2015, the Hanford site and the Livingston site, this is the noise of one interferometer, this part. This is the noise of the other in blue. But we see at a certain moment, this noise becomes the shape of a wave. And this is the same. If you subtract the noise, you see that the same waveform was seen by both interferometers. So the interpretation, the sound that we received was that we understood that it was one black hole of 36 solar masses, the other of 29 solar masses, spiraling together and then merging. We know they were black holes because these 2 big masses have rotated at 150 Hertz one around the other before merging. If they were larger objects with the same mass, they have merged much before. To stars, they don't arrive at this frequency. They merge much before. To arrive to this frequency, they need to be almost point-like objects. And at the moment of the merging, the speed was more than half the speed of light. So we have the habit to think about particles going to the speed of light almost in accelerators, but these are 2 astronomical objects. So what happened was, again, the two black holes spiraled together. This yellow part, the green part, is the crest of the wave, propagated in space for 1,300,000,000 years. This is the distance, arriving on the Earth on September 14. Also, the Earth reacted to the gravitational waves. Now, what you see here is very exaggerated, per fortuna, but this is to show that also the Earth reacted to the gravitational waves. This time, on the Earth, there were detectors sensitive enough to detect gravitational waves. So this changed our field, of course, because after that there was the paper of the discovery. This discovery gave the Nobel Prize recently to this 3 persons, Ray Weiss, Barry Barish, Kip Thorne, let's say the fathers of the LIGO collaboration. This is to show the black hole's dimension in solar masses of the big events, the first one, then also of the other. After that one, we saw others coalescing black holes. And this is, you see, very large masses. These are the masses which were supposed to be black holes due to the accretion of mass from a normal star to something very small, which was supposed to be a black hole. And we knew that because of the X-rays coming from this region, so an indirect way to understand this was a black hole. But the masses of the black holes which were supposed to be are smaller, you see, of the masses which we have seen with gravitational waves. And this year, on August 14, also Virgo was finally taking data together with LIGO, and happened a new merging of two black holes in a larger one. So this time, you see, the localization in the sky is quite difficult with the two detectors, because you can say where is the source just looking to the time delay of the arrival of the wave into the detectors. So if these are two detectors and you see the maximum time delay, 10 milliseconds, then you know this is the direction. But if there is an intermediate time, then you don't know. The locus of the point is maybe a circle in the sky, and you don't know where it is. With three detectors, you can triangulate and see where is the position in the sky. In fact, if we're only for the two LIGO, you see that this is the sky map. The position is quite indeterminate, while with Virgo, this is more certain. And this is the gain having that we have with Virgo. Finally, and at the end of my talk, of course, I have to show you what happened in August 17, not in August 14. Well, we were ready with the gravitational wave detectors to send alarms to the astronomical telescopes. This is because if a gravitational wave arrives, it arrives in some point on the sky, and you need to alarm the gamma rays, optical telescope, infrared telescope to point. Of course, you need to say them where to go, where to see. And with Virgo and to LIGO now, we can do that, actually, because we can say gravitational waves in that, more or less that direction, then all the telescope go to see what happens there, to see what develops there. And actually, this was happened in August this year. This is the press conference. This is Marica Branchesi, a GSSI researcher, who was coordinating this interaction between gravitational wave signals and the electromagnetic counterpart. Let me just show you a slide show, if I realize this. Okay. So this time there was an electromagnetic counterpart. Not only gravitational waves, not black holes. Finally was object to neutron stars merging and giving rise to a gamma ray burst, and then during the minutes, hours and days after, developing optical signals, infrared signals, radio signals. So this was really incredible, because you see, we received the gravitational waves with the two masses in the range of neutron star masses, 1.4 solar masses. Each neutron star is the sun of a supernova, is the rest of a supernova. So in a neutron star, this is compared with the Earth. It's a dimension of a big city, a neutron star. It's not a big object. So these two neutron stars, of course, they give rise to gravitational waves that we have seen, a very small amplitude but long gravitational waves, which this time arrived together. This is the gravitational waves going up in frequency, And this was the gamma ray detector Fermi. It's a satellite in the sky. After 1.2 seconds, after the two neutron stars merged following the gravitational wave signal, there was this peak in gamma rays. And this gamma ray traveled together with the gravitational waves, arriving on the Earth 1.7 seconds after. Now, this was an historical, of course, event. For the first time, we had gravitational waves and electromagnetic waves coming from the same source. So, where was the source? Well, the Fermi detector and the Fermi and Inter gamma ray detector in the sky defined very badly the position. But thanks to Virgo, we know now where was the position in the sky. And the position in the sky, interesting to see, because the reason why Virgo was so important was that it did not detect the wave, or just a little bit. This means that the wave was arriving in one of the blind spots, which are very precise. So we were able to see the region, to say the region to the optical telescopes, and they have individuated in one galaxy, in one precise galaxy, that something new happened in the hours after the alarm. What happened is that, you see, there was this dot was seen optically and fading away. This is a new phenomena. Looked and having individuated in this way the precise position in the sky. So, what was important in this measurement was that we clarified two mysteries. One mystery was the gamma ray burst. What is the source of gamma ray burst? Let me stop for a moment this show, because I want to say that gamma ray burst is something which is not obvious at all that can happen. I mean, they were discovered by satellites, spy satellites from US, wanting during the Cold War to see if Soviet Union made nuclear tests on the Earth. Nuclear tests, nuclear bombs, they emit also gamma rays, of course. Gamma rays is the signature of some nuclear reactions are occurring. So they saw gamma ray burst, but not coming from the Earth, but coming from the sky. And there was a surprise. Who constructed nuclear bombs in the heavens? So there was a mystery. What is the source of this gamma ray burst coming here and there, coming very far from the Earth, cosmological distances? So now we know the two neutron stars coalescing and merging, they cause the gamma ray burst. And this is, when I say everything's clarified, I maybe are a bit exaggerating, but this is really is a step forward in our knowledge of the universe. So neutron stars merging, they are the origin of most of the gamma ray bursts we know, maybe all the gamma ray bursts we know. The other mystery was that in the universe we have not only all the elements up to the iron that we understand are formed inside stars, but we have elements heavier than irons. We have, as you know from the periodic table, we have, for instance, this is the iron. There are cobalt, nickel, copper, but then there are gold, for instance, platinum, there is uranium. So who realizes all this? You see, Big Bang have not realized all this, but only this. And just a little bit of this. All the rest are made in stars. We thought maybe the supernova collapse is able to realize not only iron, but some of the elements heavier than iron. But all this element heavier, much heavier, was another mystery. Now we know that the merging of two neutron stars is what really builds this heavier element. We know that because of the optical telescope looking to the source that we know from gravitational waves that are two neutron stars merging. Then we know that they have seen all these characteristic lines of tellurium, of gold, of platinum, and so on. So this is another mystery. It seems that there is such an amount of gold there, which is as 10 times the mass of the Earth. So this is what we understood about the new systems. So I am at the end of my conference, of my lecture, just to say that in history, every newly opened astronomical window has found unexpected results. Starting from the Jupiter, but then also in 1912, the muon was detected in cosmic rays, and this was a surprise. No one predicted. When the radio window was opened, we have seen cosmic lunar background. We have seen pulsars. At the beginning, pulsars were thought to be some extraterrestrial clocks giving signals. And then X-ray, gamma ray, I said you. So gravitational wave window is recently opened, and we have seen big black hole mergers, much more black holes than we thought before. So the question which is now on the table is, are there so many black holes to explain even the dark matter and to solve another mystery? This is an open problem. So Virgo and LIGO have planned to go to better sensitivities. There are plans for underground detectors to reduce seismic noise and see even other sources. There is a fantastic, fascinating project to send an interferometer in the sky and look to a frequency range much lower and to see big, for instance, supermassive black holes emerging. And finally, this is the global plan of the Gravitational International Committee to have a lot of physics from the present advanced detectors, to have a project of an underground detector much larger, and to send LISA in the sky. So we started with the notebook for Galileo, the beginning of modern astronomy, the astronomy with the electromagnetic waves, and we arrived to a new sense, to the hearing of the universe. So we now have another messenger to tell us what is in the universe. And as Marcel Proust said, the real travel is not important to have landscapes or postal cards, but to have new eyes, because then nothing will be as before. Thank you for your attention.